this like 30-second delay, as I mentioned last time. So like it helps my paranoia a little just to double check if
Right.
it's actually live or not. So I'll give it a few seconds.
How many platforms are you broadcasting to?
Two.
Hmm.
I can see myself on YouTube, and this time there's no issue on the platform as well because I heard a double echo. Awesome.
Nice.
Welcome back, everybody. Great to see you all joining. The real host, Wade, and I are back. We're here to study about Hugging Face and NLP. Wade is the real host. He'll be teaching us more about these things. If you're joining us for the first time, we've been learning about the Hugging Face course, and Wade has been blending in Fastai and teaching us best of both worlds. He's an expert at this. He's created the Blurr library. So, welcome back or welcome to our study group. This is the second session in part 2 of the series. So, there was another part people were asking about it. We'll be learning about how to use fast tokenizers and NLP with FastAI and Blur. That's the title. Broadly speaking, last time we learned about datasets. With that, I'll hand it over to Wade, who's the real host. And please, as a reminder to the audience, please keep the questions coming. I'll actively monitor the chat throughout.
All right, awesome. Thank you, Sanyam. Good to be back again. Let me share my screen here. All right, hopefully everybody can see the
We
good
can.
slides. So yeah, as Sanyam mentioned, so this is week 2. Last week we looked at the datasets library. And so if you missed that one, the recording is up there on the events page. And you can go back and watch that on YouTube. And again, it's a pretty dense, all these chapters are dense. So when I went through part 1, it usually took me a few days to get through a whole section. Whereas with part 2, I found myself like having to spend like a full week and every day committing, an hour of my time to really getting into it because there's so much there. And that's true of data sets, and it's going to also be true of tokenizers. So
Even though the text is so small, you feel like it's the same in size. It's like
right.
probably the equivalent of part one, and then you realize maybe my brain is slow these days. What's going on in my
Yeah,
life?
yeah. So it was funny because when I started going through the data sets part, I kind of assumed that the pace would be the same, and I actually tweeted out to Louis Tunstall, who did most of that section, and I was like, "Man, this is so great! It's one of my favorite parts of the course." But man, there's a lot of stuff in here, and so I hope that even as we go through the study group, that you're encouraged to like go back and actually go through the official course because we're not covering everything. We're covering things mostly related to FastAI and preparing our data sets and building data loaders and training with FastAI. So please go back through the course as well. So anyways, let's go ahead and get started with session 2. And so we're going to be looking at section 6 from the course, and that is essentially going over the Hugging Face tokenizers library. And again, a lot of content. There's things that we won't be covering in the study group, such as training a tokenizer from scratch. But I would really recommend if you're working with a low resource language, or you want to actually build a mass language model or causal language model and create your own kind of pre-trained checkpoint, even for English. It's worth kind of going through that chapter and seeing how that's done, because those are really the basis. When we use one of these pre-trained models, somebody actually has done that work for us, and the tokenizers library, and alongside actually with the datasets library to get a corpus to train on, have really made that easy to do. So if you are working with low resource languages, try it out. And if you need help, feel free to hit me up on Twitter or email. I'd be glad to help and see how that goes. So we're going to be looking at the tokenizers library, and primarily we're going to be looking at how to choose the right tokenizer. There are factors. There's different types of subword tokenizers. There are pros and cons to using pre-trained architectures with pre-trained tokenizers. So we'll look at that, how to choose maybe when you do want to actually fine-tune or train a tokenizer from scratch. And then we'll look at some of the preparation required for getting a Fastai data block ready for 2 tasks that are mentioned in chapter or section 6. The first one's token classification, which is things like name entity recognition, trying to, there's a couple examples like with learning the actual grammar, like what each word represents, a noun, a verb, adverb, whatever. So we're going to look at how do we actually get a data block so that we can create data loaders for training. And we're going to do the same with extractive question answering. And also, just as a side note, a lot of times when you read about question answering tasks, they don't include that word extractive, but there's actually 2 types of question answering tasks. There's extractive, which is the answer exists in a context that your model's allowed to look at. And then there is kind of more dynamic question answering, which is the answer's not in there, and you have to train a model that can actually articulate an answer. And that task is a little bit more similar to like the summarization or text generation tasks that we'll be looking at later on in the study group. So again, we're going to be looking at how do we get those data blocks. And then the next 2 weeks, we're actually going to be looking at building off of that and actually creating a token classification model next week. And then the following week, doing an extractive question answering model as well. So again, resources, these slides will all be available. I won't spend time going through all this again, but tons of resources for Fastai. The book's excellent. The course, absolutely brilliant. Zach Mueller's Walk with Fastai will answer all those little questions that kind of come up in your mind as you go through the official material. And then there's several Fastai Hugging Face libraries. I created Blurr. That's one I'm most familiar with, and the one that I'll be spending the most time going over in this study group. But just know there's other ones out there, and this may not be exhaustive. So if you're aware of other integration libraries, let me know. Okay, so let's go ahead and get into the first question, which is choosing the right tokenizer. So just like there's advice about using pre-trained models, you want to use as much as possible a model that's trained on a task that you're trying to accomplish on a corpus or that has been pre-trained on a corpus as similar to yours. And this is important all the way down to what tokenizer, what the corpus that the tokenizer was trained on, and maybe even the type of tokenizer. And so if you're using a tokenizer that was pre-trained on a corpus or another domain or language, that's typically not going to work very well. And so the example they give in the course is if you're using a tokenizer that was trained on an English corpus for to be used against a Japanese corpus, it's probably not going to work well because of how the characters and also just how spaces are used in English versus Japanese. And you can even think about it even within a language. If you're trying to create, let's say, a sequence classification model, and you're using a pre-trained architecture, right, that was trained on, let's say, survey comments, and then you try to apply that to another corpus that is basically composed of tweets and retweets, it's probably not going to do as good of a job as if you actually had a tokenizer that knew how to handle like the @ symbol and the hashtags. And so again, this happens because the use of spaces and punctuation varies because of the introduction of new characters, domain-specific verbiage, and or styles. And again, remember, the tokenizer is going to create tokens. And from tokens, when you start training your model, you're going to have learned embeddings. And those learned embeddings are essentially numerical representations of your tokens. So if you're using a tokenizer that breaks up really common words, you're probably not going to have it as good as a representation if those words were actually put together. And we'll actually look at a few examples right now. So let me pull up this notebook. And I'm installing all the main libraries again. This notebook will be made available later, and we're looking at the 2.0 branch of Blurr. So let's look at choosing the right tokenizer. So one of the examples they mentioned in the course is this dataset code search net. And again, one of the cool things with datasets is that you can probably find a dataset in there that's pretty similar to what you're doing. So here's one that actually has examples like pieces of code, and you can actually specify essentially like a subgenre, like what language you want to look at. So we'll look at Python. And here again, because I'm just using this for illustrative purposes, I'm going to just load the first 1,000 examples from the training set. And we can kind of look at what one of those examples looks like. And, pretty traditional Python, right? So you have, here's your method definition, the name, you got like ** quargs, a new line, and then you have indentation, docstring, etc. And so the best way to really figure out if you're working with a good tokenizer, if the architecture you've chosen and the tokenizer you're using is going to work well for your task, is really just by looking at an example. So if there's any questions, look at the example. And so it's easy. I can pull up this example, tokenize it, and you can see this is the result, which isn't really optimal. Like, it didn't really capture common grammar in this particular corpus because it wasn't trained on Python code. And so you can see, like, this is new line, this is a space character. And so instead of grouping the spaces and new lines, it actually just broke them up into individual characters. And it would probably be helpful to really recognize what those pieces are together, and to create a representation for new lines and indentation, because it tells you kind of what part of code is related to the code around it. So it really didn't do a great job. And so this would not be probably an optimal tokenizer to use for looking at Python code. And you can see it's quite verbose because we have all those spaces, right? So it takes a lot of tokens to represent an example. And again, that's bad because most of us don't have, a bunch of high-end RGB loving DL rigs at home with, quad GPUs and parallel processing abilities. Most of us are working on Colab or working on a local DL rig. And so things like this, like, we can only process maybe 128 tokens at a time. And so we really are requiring a lot of tokens to represent this particular example. It'd be nicer to have less tokens. It would probably make our models more efficient and more capable of looking at whole examples without having to truncate it. And I saw Sonia pop on there real quick because he's got, these, like, some of the most amazing, like, machines I've ever seen. So anyways, so yeah, this didn't do a really great job with the Python code. And so again, we might be tempted to go, oh, GPT-2, that's a common one. Let's just go ahead and use it and train it. We probably wouldn't get good results. So again, if you're not sure, look at an example. Another thing that I typically do is actually look at the papers. And you'd be surprised, if you haven't read an academic paper or an archive, how easy it actually is to get the main gist. There's a lot of the latex and the math and the Greek that is foreign to me, and it's easy to look things up. But overall, just reading the description and some of the high level parts of a paper in terms of why they went with the approach they did, what corpus they used, their results, could be really helpful in determining at least what kind of architecture and pre-trained checkpoint to start with. So like for me, I'm only really working with English corpuses, and like I've learned that to generally trust using a Roberta or a dBERTA architecture for like sequence classification, or I'm a big fan of BART, and I use BART for and have really good results for sequence classification, token classification, and summarization. And so as you start to use these different architectures, you can also kind of get a feel like, which one's going to work better for your task and for your corpus. So if we wanted to, just like we can fine tune a model, we can fine tune a tokenizer. And so this right here is going to create a generator for us that's going to work just kind of like how a data loader does. It's going to give us a mini batch of text examples to feed into our tokenizer for it to train. And you want to define this as a function because once you use this, you're one and done. So you want to have it as a function you can call repeatedly. And there's different syntaxes for using a generator. I prefer this one. To me, it's more readable. It's more flexible. And if you're not familiar with this yield keyword, I would advise you to Google it and get comfortable with it because you'll see it not just in this example, but you'll also see it in Fastai in several places. And you'll see it in a lot of libraries wherever they're building data loaders, because again, we're yielding batches at a time. So if you're not familiar with that syntax, check it out. But it actually is really easy. It's kind of amazing to me how easy it is to train or to fine tune a tokenizer. You really just need to take the corpus. We have our tokenizer object, and they have this nice method called train new from iterator, where you pass essentially your generator, and this is the number of items you want in your vocab. And we're working with the subset, and it's super fast. And so I can imagine even with the full corpus, it's unbelievably fast. Really impressed. This actually kind of is very fast AI-ish to me because, I mean, with one line, you can train or fine tune a tokenizer, for your own corpus. And you can see that once we do that, we get a lot better results. So in particular, notice that there's less tokens. There's still a lot, but there's a lot less tokens required to represent that example, which means that we're going to have to truncate less data, which means we're going to be able to train locally or on Colab, and be able to have much more text in there. We'll be able to have bigger batches. And also we're going to have better representation. So it's kind of learned like this is a common thing it sees. It sees a new line with a couple indentation spaces. So it's actually starting to learn like really key parts of our corpus, which is nice. So again, if you want to fine tune a tokenizer, it's that easy. We can also look at like tweets. So again, I just went to the data set, saw this tweet eval data set. And tweets are interesting, right? Because they got these little funny hashtags, and they also have like this particular set. If there's an @ to a user, it just replaces it with @user. And so we can look at like, okay, how does GPT do on this? And you can see it doesn't really understand like this right here. This hash tag should really go with this word, right? And also with @user, it doesn't really associate the @ tag with user. So it did an okay job. This actually may work, but not really. It's not really optimal, right? And so just like before, if we wanted to, again, create our generator, take our tokenizer, train from new iterator, and then we can go ahead and test it. And you can see that it still kind of didn't do a great job. The GPT-2 or GPT-2 tokenizer didn't do a great job. But it did kind of group the things, right? This hashtag goes to tinypic, and here's tinypic. So it's seeing that that's a common word in this corpus. It still kind of missed this. And part of this may be because of how the tokenizer works. So I have a feeling the GPT-2 tokenizer, which is a byte pair encoding tokenizer, we'll look at that in a second. I have a feeling it splits on kind of weird punctuation like that just by default. And so this might mean that instead of fine tuning, what we should do is create a tokenizer from scratch and not include that splitting on punctuation as part of our pre-processing. And again, the course actually goes through how to create 3 different types of tokenizers. It's really interesting. And so if someone wanted to do this as homework, that would be really cool, and especially if they share it in a blog post. So we can also try a unigram tokenizer, right? So we can pull up T5, look at that and see how that worked. And one thing with T5 is that when we train the tokenizer, is that notice it actually learned to group the hashtag with the thing that it's related to. So even T5 looks to actually have captured how, or which is a unigram tokenizer, sentence piece tokenizer, actually, in my opinion, is able to better represent tweets. So if I were actually examining this corpus, I may look at using T5 and finding a good pre-trained checkpoint for that. So that is how to essentially look at a tokenizer and determine whether the one you're using is good. Look at an example, look at the paper. If you're really in trouble and you can't find one, then you can either fine tune or you can train a tokenizer from scratch. And again, in the slides, I linked to the last subsection of section 6. And there's an example of building your own word piece, BPE, or unigram tokenizers. So pros and cons of training your own. If you train your own, remember, you're actually changing the vocabulary, which means that the embeddings that a pre-trained checkpoint will have included in their weights that have been learned won't be available to you. So you're going to have to train your own language model. And another con is if you're experimenting with multiple architectures, which is typically something I do, you'll have to train and fine tune the tokenizer for each if you go that approach. The pros are you'll have a better word token representation for your corpus. And we saw that when we looked at the code sample and how it's able to understand indentations, how it's understand spacing in the Python code much better than the default GPT-2 tokenizer. So in summary, my advice is to try avoid training and fine tuning. Look at the papers, look at the hub, try to find something as similar as possible so that you can avoid having to go through building your own language model. And frankly, there is so much stuff on the hub. I would be really surprised if you have to go this route. I'm sure for low resource languages, it's still something you may have to look at. And if you do that, you will have the gratitude of the entire Hugging Face community, especially if you share that on the hub. But as much as possible, try to find a checkpoint that was trained against a corpus that's at least fairly representative of what you're trying to do. And there's also a good description of, these are all subword tokenizers. So this isn't exhaustive. There's other tokenization strategies used by some transformers, but these are the big ones. And so I included this in the slides just so you kind of know not just how they're trained and how they work, but things to keep in mind. Like one, which is really nice, and probably one of the reasons that Roberta and Bart and DeBerta work well for just about everything that I do, is that it's impossible to get an unknown token when you use byte level BPE. Unc tokens are basically the tokenizer's way of saying, I see something, I don't know what it is, so I'm just going to call it unknown. And as you can guess, having unknown tokens are not good because there's really nothing helpful that your model is going to be able to learn in terms of representing unknown tokens. So you want to avoid them as much as possible. And one of the nice things, again, with these byte parent encoding, these byte level BPE tokenizers, is that you don't have to worry about getting an UNC token. You'll never get it. With Blurr, Funnel, and PNet, these represent word piece tokenizers. It's possible to get unknown tokens. For Unigram, some example architecture would be T5, Albert, XLNet. These are all use a particular form of Unigram, which is called sentence piece, which is really common. And so just as a note, it never removes base characters, so as to ensure any word can be tokenized. So I think it's almost rare to never that you're going to get unknown tokens here. Not absolutely sure about that, but I'm pretty confident that's right. And then also, one of the nice things with sentence piece, there's two nice things with using sentence piece based tokenizers. One, because it doesn't have a pre-tokenization step, it's really useful for languages where the space character isn't used. So if you are using something like a Chinese or Japanese corpus or something similar where spaces aren't used to denote words, sentence piece could be the right place to look. The other nice thing with sentence piece is that it is fully reversible, which means that you can tokenize your corpus, and then from that tokenized corpus, get back to your raw text one for one. This isn't necessarily true with all tokenizers. So like Blurr, for example, will remove repeating spaces. So if you tokenize a text with a Blurr tokenizer, repeating spaces are going to be removed so that when you go to decode it, you're going to lose that, which usually isn't a problem, but just something to be aware of. So again, if you're using a language like Chinese or Japanese, maybe kind of focus your exploration on unigram and in particular sentence piece tokenizers. And with that, is there any questions coming up yet, Sanya?
I'm just curious what happens if you like try to tokenize emojis.
I was looking for just a data set of emojis, and I think there are examples in there. But yeah, that would be kind of interesting, right? In terms of how they group that, because I mean, emojis are all just kind of punctuation, right? Kind of weird punctuation. And so I have a feeling that by default, most of these tokenizers don't do a great job with it. That's my gut feeling. But I also have to believe on the hub, there are some pre-trained models, some folks that already did this hard work, because it's so common, right, to see them nowadays.
It's weird, like because all of these models are trained on, I think, Reddit and similar corpuses, which
Yeah.
don't have as many emojis. But in our chats, at Bits and Biases, we have this like Slack allows you to check the emoji reactions. I'm on the top of the leaderboard, so like I'm I use a lot
Why am
of
I
it.
not surprised? Why am I not surprised?
But yeah, I think there should be some people who would have put up stuff.
Yeah. No,
There's this.
I'm not surprised you're on the leaderboard, and I have a feeling the most common one is the chai emoji that I've seen trending, recently.
Yeah, you might be 100% accurate about that.
Yep.
um, Korean is asking if you could go to the tokenizer output. What is the G like thing he asks in the output there?
Yeah. So when we looked at the, let's go back that real quick. So again, each tokenizer has different ways to delineate things like spaces or new lines. So if we're looking at like T5, you can see it does it with this underscore character. For GPT-2, uses these kind of funny, I'm not even sure what that character really is, but the G right here is how it represents a space. And then the weird C character is how it represents a new line. And so it's actually, you kind of see this more when you get up here. So yeah, like right here, you can see this is the end of the method definition, right? In Python code, and it's followed by a new line. 1, 2, 3, 4, 5, 6, that's 7 or 8 spaces, and then the doc string. And so, yeah, so that's a space, that's a new line. And then, yeah, you can see, so there's actually 8 spaces, right? Because there's another new line, and then it learned, hey, these 3 double quotations are important in this particular corpus.
Thanks for that. There are no other questions, but again, reminder to all: please keep asking the question. Then I'll interpret whenever I get a chance to ask them.
Cool. All right. So the next thing that's heavily discussed and is used throughout Section 6, and then also into Section 7 when they start looking at particular tasks, is there's 2 types of tokenizers. There are fast tokenizers and there are slow tokenizers. And the fast tokenizers are written in Rust. It can take advantage of parallelization. So we've seen, like in prior study groups, how much faster they can process our text, tokenize it, and give us all of our various inputs. And then the slow tokenizers are written in Python. They are slow, and they also don't have as many features as fast tokenizers. And so one thing is when you're building an architecture, I will say that by and large, there's a fast tokenizer version of the tokenizer that you want to use. And when you call auto tokenizer, if a fast version exists, that's what you're going to get. And as a recommendation, try to stick with fast tokenizers. We'll look at some reasons why they definitely make tasks like token classification, the pre-processing and post-processing much easier. Same with question answering, same with building mass language models. So try to stick with the fast tokenizer if you can. And when we go look at Blurr, I'm really building things out to mostly work with fast tokenizers. But if you're not, you can substitute and provide functions like that can provide things like word IDs, which we'll look at in a second, which is something only a fast tokenizer does. But if you create a function that does that for a slow tokenizer, which is possible, you can still use Blurr to its fullest. So why fast tokenizers? One, that fancy train new from iterator method to fine tune a tokenizer only works with fast tokenizers. As I mentioned, fast tokenization, when we tokenize text in batches, can be parallelized, and it's just by default, it's parallelized and super fast. The other thing that is really nice with fast tokenizers is that they keep track of the original span of text, or the characters the final tokens come from. And this allows us to do a lot of things that are really helpful for the two tasks we're going to be looking at. Things like mapping each word to the tokens it generated, or mapping a token back to the original text and the characters. And this all happens by looking at the batch encoding object that's returned when we call the tokenizer. And one of the things I always have asked, like on the Hugging Face forums, and I put here in the text, is there's actually a big table that lists what fast tokenizers exist. So see this slide and click on this link down here to check that out for yourself. So let's go ahead and get into some of the pre-processing side. So again, this week we're looking at, okay, let's get our data loaders ready. And then next week and the following week, let's go ahead and take what we've done this week and actually use it to train a token classification and question answering model. So some of the things that fast tokenizers provide that are real helpful in token classification is, one is this idea of word IDs. And so again, when tokenization happens, it takes words and it breaks them up into subtokens, right? So there's one or more subtokens for every word in your raw text. And when you're doing token classification, we have labels like person, organization, location assigned to a word. And so it's really helpful when we're encoding the subtokens to use this information, this word IDs, to know, like, okay, here's 3 subtokens for this one word. What's that label for that word? And given that, how do we actually label these subtokens? And there's different strategies for that. The other thing that's really helpful is this return offsets mapping equals true option that we can pass when we call our tokenizer to tokenize a batch of text. And we can use this to, again, apply the label properly to the predicted or assigned token, and also use that to, when we're decoding our subtokens and decoding them back into words, to figure out what we're going to choose as the correct word. And again, there's a couple different strategies for doing that with token classification. So let's go ahead and look at an example here. And I'm also going to show you some Blurr code as well, so you can see how this is all happening. But if you wanted to basically use Blurr and Fastai for token classification, this is how you could do it. And I'm going to go ahead and use the NLL 2003 dataset, which is really nice because it actually includes several token classification tasks that you can choose to run. So we have a POS task, a chunk task, and a name entity recognition near task. And we can kind of look at like what the text looks like. And we can see that we're working with label indices, right? So these label indices point to these particular labels. And so we can see for the different tasks here, like what these things actually look like, what we're trying to predict. And so you can play around with, like I said, different token classification tasks just with this one data set. So we'll look at using the name entity recognition tags. So these are the labels right here. And again, for just about every Blurr task, it's really, you want to get your Hugging Face objects, the architecture, the configuration object, tokenizer, and model. And almost everything can just be fetched using this type of syntax right here. So I'm going to choose as a pre-trained model name is Distill Roberta Base. This is one of my favorites because it's Roberta, which is a fabulous architecture for just about anything classification-wise, including token classification. And the distilled version is really fast. So I can actually use bigger batches and use a bigger max length, whether I'm training on Colab or on my own local DL rig. So we go through this process, we get our objects. The key configuration to pass is the number of labels. This is probably the most frequent mistake that folks make when using Hugging Face and using the Blurr library, is that they forget to set this. And by default, it's 2. If you have anything more than 2, you'll get some interesting errors. They're sometimes not that readable. A lot of them look like those CUDA assert errors that are real fun because they tell you nothing except that something is seriously wrong. So just remember to set that when you're doing token classification. We can check to see if our tokenizer is fast by just calling that property as fast. And then there's cool things, again, that we can do with the fast tokenizer. So I'm passing in this return offsets mapping. And again, these are things that you can only do with the fast tokenizer. So if you want to replicate this with a Python tokenizer, you're going to have to write your own code. And that's probably going to be very specific to whatever tokenizer you're using. So again, try to use fast tokenizers if you can. And you can see that when we pass this, we get this another key added to this batch encoding object. And so we can actually look at the tokens. So again, when a tokenizer takes our raw text, it's going to create a list of tokens, which is exactly what we see here. And for Roberta, we have, this is our class and our separation token. And you can actually figure out what all these are by looking at the documentation, or you can inspect the tokenizer. They actually list, there's actually methods to actually get and see what are the special tokens for representing separation, classes, padding, and so forth. So we can see that these are our tokens. And we can also see the mapping between tokens and words. So as an example, my name is not a common spelling of Wade, and we can see it's broken this up as that's the space WAYDE. But how do we know that these two tokens come from the same word? Well, that's what we use word IDs, and we can see that none is assigned to the special tokens. So we start with 0, 1, 2, and the third word is Wade, right? So we can see 0, 1, 2, and both of those tokens are mapped to word 3, which is Wade. So this is going to be really helpful for token classification. The other nice thing that we'll use for token classification and question answering is the offset mapping key that's added when we pass return offsets mapping equals true. And what this is actually going to do is give us a mapping back from each token to the characters from which it originated. So you can see all the special tokens are going to be just 0, 0. And we can see that this is token 1 goes from 0 to 2, token 2 from 3 to 7, token 3 goes from characters 8 to 10. So again, this is going to be really helpful regardless of whether we're working with languages that use spaces or not to figure out how to get back to that raw text. And again, token classification, this is going to be really key because we're going to break things into a bunch of subtokens, but ultimately we want to go back to our words and say, like, what is this word? It might be 5 tokens to represent this word, but at the end of the day, what is that word? Is it a person? Is it a just nothing? Is it a location? So this allows us to do that. So anyways, yeah. So we can use this capability to apply labels we have for each word properly to the tokens and tasks like name recognition or part of speech tagging. We can also use word IDs to map each word's label onto the tokens. And then we can use offset mapping to apply the labels assigned to a token back to a specific word. And so, like I said, there's actually different strategies for doing this. And in Blurr version 2, we support 2 that are mentioned in the course, and then also a third one. And we'll take a look at briefly at what those are. But it's as simple as passing in this label strategy class. And again, there's going to be 3 of them in Blurr. You can also create your own. By default, we're going to use the only first token labeling strategy. And how does that actually look? Well, here's kind of an example of the 3 strategies and how they would change how we actually represent the tokenized words. So only first labeling strategy, which is the default, the first token is going to get the word label. The other ones are going to get -100. So -100 is the default when we calculate cross entropy loss. It is the number that tells cross entropy loss to ignore that particular element when calculating the loss. And so by using this strategy, we're only going to be really determining the whole word based on the first token. And when we calculate our loss, it's going to know to not really include the other the subsequent tokens when calculating that. It's only going to do it based on the first token in the word. Another strategy that's supported is the same labeling strategy. And in this, what we do is assign each token to whatever the word label is. So again, here, Wade is the beginning of a person's name. And so we would assign B-per, B-per to both of those tokens. A final one that's fairly common, and this is the one that's not introduced in the course, is the same labeling strategy, is the BI labeling strategy. This is included in the course. If you're using B and I labels, so for example, my name is Wade Gilliam, and Wade would typically get a B-per label, and Gilliam would get an I-per because it follows on from the beginning. If you're using that strategy, we apply that further to tokenization so that here, even though Wade, the whole word is would be labeled as BPER in the raw data set. We use BPER as the first token, and then we use IPER as the following token. So those are the labeling strategies that Blurr supports. And if you go through part 6 of the course, they'll go over and also some of the pros and cons of 1 and 3, and why you may want to choose one or the other, why researchers choose one or the other. They'll both give you, they should all give you good results, but spend some time going through that if you have further questions. So yeah, so we can go ahead and we apply a labeling strategy. And the other big thing with token classification is that our inputs are list of words. And it's really critical to kind of really think about why you want that. And again, it's because, for whatever language you're working with, again, we're trying to identify what a particular entity is. And when you provide a list, it's much clearer like what that means versus just a bunch of raw text and then leaving it up to the tokenizer to create a list of tokens from that. So for token classification, it's required the input needs to be on the list. When you do inference, we can pass in raw text, and that's something we'll see next week. So again, I'm working with the data set. With Blurr, we have this HF token class before batch transform that does some special things for token classification. And next week, we'll look more at using a pre-processed data set and why that might be useful. But again, with Blurr, just as with version 1, we can go ahead and do this tokenization process on the fly. And so that's what we're going to do here. And we are using item getter to get our tokens and our NER tags, and we're just using a random splitter. And again, the ultimate goal is to get our data loaders, which when we pass our training data set, we get always a helpful thing. Look at the batch, right? Does it actually make sense to you? When I'm building Blurr, a lot of times the batch looks wrong because I've done wrong things. And this really is kind of like a safeguard to make sure, like just a sanity check, like, yes, what I see here in terms of the number of items in the batch, what input IDs looks like, what the targets look like. Yes, that makes sense. And I can go forward. And then we can also call show batch. And with Blurr, the way that show batch works with token classification is that it takes each of your raw words and it shows the label. So it shows the word and then the label associated, the entity label associated to it. So that is how you can actually prepare a data block for token classification tasks using Blurr. And I wanted to, can you guys all see this, or does it need to, do I need to blow this up a little bit? We can actually look at some of the Blurr notebooks. And again, these are all like up on GitHub on the V2 branch. Oops. Yeah.
I think you might have to zoom in a bit here.
You know what? This is going to sound really ridiculous, but do you know how to zoom in? Oh, here we go. I don't know.
That disappeared.
That was an interesting side effect. Let's try that again. Zoom. Is that like any bigger to you? No. Oh, here we go. Oh, nice. All right.
Awesome.
There we go. Much better, I hope.
Yep, that's awesome.
Yes, you can actually look at all that stuff that you saw in the use case of building a data block for token classification. If you go to the notebooks, you'll see how all this stuff works and how it's utilizing some of these fast tokenizer bits. And so you can see how there's labeling strategies. And again, if one of those 3 labeling strategies doesn't mesh with what you want to do for some reason, you can actually create a subclass of base labeling strategy and use your own. And if you look at these, you can see that they're all using the word IDs, right? So being able to take these tokens and figure out what word they're associated to get the label, whether it's going to be using the same label for each token or use the BI syntax or set the subsequent tokens to -100, you need to be able to work with word IDs. So you can go through this code and actually, hopefully it's pretty readable and see how those different strategies are implemented in practice. There's also, and we use this in the show batch method, but you can actually use this on your own. We have some other methods like get token labels from input IDs that allow us to, as best as possible for the tokenizer, reconstruct the original raw text. And this is really helpful when we're doing things like inference, right? And we don't have things pre-split up necessarily. And so you can kind of read how we do that. A lot more tests in Blurr. So one of the nice things, I use NBDev for building Blurr out. And it's nice to be able to include these tests right in the notebook. And so you can actually pull up these notebooks, run them yourselves, verify that the tests work, and have confidence that you're getting what you expected. And then we have get word labels from token labels. That actually works in conjunction with the method that we just saw. And so check that out. That's all has testing associated with it. Next week, we'll look at pre-processing. So I'm going to skip that part right there. And then you can see that for Blurr, we have a mid-level API. We introduce a couple of target-specific elements. So we have a token tensor category to identify token classification inputs. We have a HF token categorize method, because we have like basically what this does is turn every single input into a category that we want to predict. Check at that. And then again, just like we have the text input, the HF text input block, we can create blocks for our targets. And you can see it's fairly simple. It just really wraps that HF token categorize and presents that as a type transform. Let's see here. Oh, so again, because we're really relying on fast tokenizers and these methods like word IDs or like the offset mappings, in some cases, I didn't want to preclude people using a slow tokenizer from using Blurr. So what you can do is provide your own slow word IDs function. And it just needs to return the same things that a fast tokenizer's word IDs would. And if you do that and using a slow tokenizer, you'll see like here where I'm needing to get word IDs. If the tokenizer is not fast, it's going to call that method you provide, and that method should receive the tokenizer. It's going to receive like what the index of the example, and then it's going to receive that batch encoding object, which isn't going to have as much as it would with the fast tokenizer, but will have enough for you to essentially hopefully be able to return word IDs. So if you actually work through any of those examples, again, that'd actually be really fun to see, like in a blog post. And also, if it doesn't work and you have problems, that would be good for me to know about as I develop the library. So yeah, feel free to check out the documentation and explore this on your own. And is there any questions on token classification?
There are a few questions. So the first one is how is fast tokenizer different from Spacey under the hood?
So yeah, so with Hugging Face, we're not using any of the Fastai tokenizer like that uses Spacey. So Spacey is a little bit more. I'm not 100 super familiar with using it, but I think it operates more like on Spaces. So I don't know if it's friendly for as many languages is like a subword tokenizer would be. But it's really been a long time since I played with it. I know there's equivalents, right? There's Spacey versions of Spacey for different languages, right? That you can download. And I don't think the way Fastai is set up, it's really going to work well with languages that don't use spaces. And really, I don't think it's going to be set up well to work with non-English text by default. But yeah, what all the particular differences are, I'm not positive.
Okay, that makes sense. Thank you. Isn't same labeling strategy wrong if we use same always, as B dash denotes start of sentence entity?
I think it just depends. To be honest, I have typically used the same labeling strategy, and I have gotten really good results. It's definitely not one of the traditional ones. So in the course, it uses the first token and then also the BI strategy. But and maybe this is before I just knew any better. I always used the same labeling strategy so that each of the tokens had the same label as the word. And like I said, I actually got really good results. And ironically, I actually trained a name entity recognition model on a German corpus that ended up working really well for English
Fantastic.
broad text. And I think there's a lot more similarities between German and English, right? Like some of the words are very similar, if not identical, and also with the spacing. But it was kind of amazing that it worked as well as it did. So yeah, you're right. That's definitely not one of the normal ones, but it's the one I've used in the past and had good results. So I'm including it in the library.
Awesome. Thanks for sharing that.
Yeah.
No, I don't see any other questions. So I think that was the last of it.
All right, cool. All right. So that is it for basically, we're at the point now with tokenizers, we can actually create data loaders. And again, next week, we're going to look at actually using them to build a model. So the other task that's mentioned in section 6 is question answering. And so one of the things that's interesting with question answering is this quote that's in the material is, unlike other pipelines, which can't truncate and split text that are longer than the maximum length accepted by the model, and thus may miss information at the end of the document, the question answering pipeline can deal with long context and return the answer to the question, even if it's at the end. And so this kind of comes up pretty frequently in conversations about Blurr and question answering as a whole, is that how do you deal with long text? Because typically we truncate things, right, to get whatever we can to fit on our GPU. And so with question answering, we can actually use this other parameter to our tokenizer called return overflowing tokens equals true. And we can do this when calling our tokenizer. And what this will essentially do is, if our max length is 128 and we're dealing with an example that's 1,000 characters long or whatever, it will actually chunk that into just 128 max token chunks. And so one example will actually be chunked and converted into multiple examples. And that's something that we can do when we're doing question answering. And that alleviates this idea of maybe missing answers that are at the end of long text that would otherwise be truncated. So we'll look at that. And that's particularly helpful when you're pre-processing, because one of the things you want to do when you train your model and you score it, and you're trying to figure out, like, okay, we have this one example that's broken up into 10 chunks. Which chunk has the best answer? You're going to want to be able to figure out, like, all those 10 chunks are part of a single example. And so this really only makes sense when we're pre-processing our data, so that we can assign the unique ID associated to the example to all 10 of those chunks. And so basically perform that task. So that's something we could do with question answering. The other thing that's helpful is with fast tokenizers, which I'm annotating with this little asterisk. That's a fast tokenizer thing. We can access the sequence IDs for a particular example. Because when we're trying to figure out where the answer sits in our tokens, we don't want to have it look at the question. And so we can use sequence IDs, which is going to tell us, because we're passing in a question and a context, we can say, mask all the tokens associated with the question part. So when you're looking for an answer, this is where you should be looking. And again, this return offsets mapping equals true to be able to convert token positions into a span of text. So especially as we're going through example by example, whether we're using the overflow tokens and chunking things or just truncating, we want to be able to know what tokens are associated to what characters, because in most of our question answering data sets, what we're given is the index of the start character where the answer is, and then what the answer is to figure out the end character. So we have to be able to go back from raw character indices back and forth to token indices. And so with return offset mapping equal true, we get that offset mapping key in our batch encoding object. We can use that to accomplish it. So let's take a look at what that would look like in terms of using Blurr. So for this particular task, I'm going to use version 2 of Squad, which is a really common data set. And there's some variations that are interesting that include like no answers. And this actually is the one that has like some that are answerable, some that aren't. So definitely this is kind of the go-to to kind of learning question answering. And you can see I'm going to use some of the fun data set stuff we learned last week. I'm going to convert it to the format, underlying format to, or not the underlying format, but I'm going to have it essentially act as a pandas data frame so that we can actually look at this in a little bit nicer format. And as you can see, this is pretty common with most question answering data sets. We get a context, a question, and then an answer. And notice in this case, answers is actually a dictionary, and it has a couple things in it. It tells us what the answer is, right, in the late 1990s. And it also tells us the index of where that answer is, where the start character is in the raw text. So it's at position 269. So we're going to go ahead and use this particular format, and I'll show you how to set up a data block for this. And notice if your data doesn't come in this format for answers or whatever, that's fine. This example will hopefully kind of give you some inspiration about how you can still get this data and put in a data block that will work the same way as it will for this particular example. So we're going to get our Blurr objects. And notice that this time I'm going to set a max sequence length, and I'm going to set to 128 tokens. And this is because in question answering, our model is going to try to predict the start token index and the end token index of the answer. And so if you think about this, like from like a Fastai standpoint, we're actually trying to perform two categorical classification tasks, right? We're trying to predict the start and the end. And so we need to give the Fastai, we need to create multiple category blocks. And the categories are going to essentially be one prediction per token position, right? So we're in token classification, we're looking at every token we want to get a prediction. We'll mask out things like the class or padding tokens, things that we don't want to include. But at least when it comes to our raw data, this is how you want to think about it. We're trying to predict, for every example, 128 predictions. And notice that we have two category blocks. This one right here is for the start position. This one right here is for the in position. And for every example, we're going to have 128 tokens. And so we're going to have 128 predictions. Now, if you notice, this block looks kind of interesting because I also include a none block in there. And the reason is that I'm going to structure things so that not only can we predict the start and end location, but we can actually have another target we're trying to predict, which is whether or not the answer exists in the example. So you don't have to do it this way, but I'm going to show you kind of a way to do that. And again, because we're doing things dynamically, I'm just going to set this to none. And then when we actually construct the data block, I'm going to actually create the value that we're going to use in this place, which is going to be a Boolean, right? True or false. And the way I'm going to do that is by using this method right here. And this method right here is actually going to return a tuple of 3 things. So first, this is kind of straightforward, right? We're passing in 2 things as our inputs, our question and our context. And then our target is going to be composed of 3 things. And this is actually going to, we're going to change what these things are as we actually use our before batch transform for question answering. Because right now, since we're doing things on the fly, again, next week we'll look at a pre-processed example that we don't have to figure this out. But notice that for the start and end, we don't know what those are yet, right? So when we're doing on-the-fly tokenization, those are things that we'll find out when we tokenize. If we were using a pre-processed text, we would know what these are. We wouldn't have to use these particular methods or attributes. But here, we're not going to actually know what the start and end is until we actually tokenize the data, which happens on the fly. So in Blurr, I provide this get dummy token index that you can use. It basically is just going to return, I forget, it's like 1 or 0, but we're going to replace it. And this is just to get the data block to work. And then notice that for the get y, this is actually going to return a tuple, which is going to have, as we saw when we looked at the raw data, we're going to break this out and have the answer text, the start character index, and the end character index. And then we're actually going to use this within Blurr to figure out exactly whether or not the answer exists, and to also update the real values for our start token index that we want to predict and our end token index. And we'll look at Blurr to show you how this works. So it looks a little bit more magical than it really is. The other thing that's key is that you need to pass this to your data block, which tells you how many inputs. And even though we have 2 inputs, these are actually just going to be one thing. And so when you tokenize things like this, you tokenize a question and context, or sentence 1 and sentence 2, it really returns a single set of input IDs for both of those. So we need to tell Blurr that there's going to be 1 input, and then it will know that everything else is going to be a target that we want to predict. So once we do this, we can then call .data loaders. We can look at our batches, and then we can actually do a show batch. And the way show batch works for question answering is that it's going to tell you whether it was found. It's going to tell you the start and end token indices, and also what the answer is. So by show batch, we can go through, and you can see that some of these, because again, I'm using on the fly batch time tokenization, I'm truncating to 128. And the reason some of these are false is because I actually truncated the text so that the answer no longer exists. Like I said, next week, we'll look at using that strategy of the overflow tokens to break up long documents. But if you don't want to do that and you just want to truncate it, then this could potentially be a problem that you're going to find as you start training things. So, so anyways, yeah, that's how it works. And then if we look at the code here, and I'm going to go not look at the pre-processing at this point, but I want to look at the before batch transform. You can see, so remember that we're passing in those dummy values for a start end, and then we're passing in that tuple, right? That's really we want to use for the has an answer that includes the actual start character index and end character index. And you can see that if you're not using a pre-tokenized data set, which means pre-tokenized means we've already calculated what those are for our particular tokenizer that we're using. If we haven't, then we want to do that on the fly. And so you can see we're using the sequence IDs method, right, to create a mask. We want to mask the question mask so that that's not considered when we're figuring out whether or not our particular example has the answer in it. And then we call this method, which is part of the Blurr library, which, given a tokenizer, given your targets, and given your input IDs, offset mapping, and question mask for a particular example, can go ahead and find out, okay, what is the start token index that the answer is for the answer? What's the end token index? And of course, is there even an answer? And then, as I said, we're going to replace, remember, there's 3 targets that we create in our data block, and they're just dummy values essentially right now. We're actually going to update those to be the has answer, the start, and the end token index. And if we go to find answer tokens, you can see how that process all works. Essentially what we're doing is we're using that offset mapping that we mentioned earlier, right? That allows us to go from characters to tokens back, or from tokens to characters, to actually figure out, okay, we have the character start and end indexes, but what are the token start and indexes? And we're essentially going to use that information to figure out where the answer is in reference to tokens rather than characters. If it can't find the answer, it just returns a tensor with the value 0 for both the has answer, the start, and the end location. So feel free to spend some time looking at this. I'll probably be adding some. I had some tests originally. I think I might have taken them out, or they're hidden somewhere in my blown up view of the screen. But I'll be adding some tests to verify, and so you can have confidence that this find answer token indexes works correctly. But that is basically it. Next week, we're going to look at, with regards to question answering, is actually using a pre-processed version that has that chunking in there, so that we can handle long documents. And you'll see that it makes the data blocks a little bit more easier to work with. And then we'll also kind of look at how to score these things correctly. So there's when we're working with chunked examples, so examples that have been broken up into multiple examples, it changes how we need to process our validation set. So we will look at that next week. Any questions on question answering?
No questions so far.
All right. So for homework, go through part 6. There's also a really good end of chapter quiz. It was like really will test your knowledge of different types of tokenizers and how they work and their pros and cons. So see if you guys can pass that. See if you can actually use some of the content that we talked about today to create a data block for a part of speech. So a little bit different than name entity recognition. See if you can do this for extractive question answering. As Sanya Moy says, teach others what you've learned. Blog, Twitch, whatever. And as a bonus is go through the parts in chapter 6 and see if you can create your own word piece or unigram or BPE tokenizer, especially if you have a low resource language. But even if you want to just try to do it with an English corpus, to get an idea of like how folks have gone before us to actually create these checkpoints that we're all using for these other downstream tasks. So, and if you do that, I'd love to see what you've done. So let me know. And if you need help, give me a holler. And I think that's it for me.
Awesome. It's really fascinating to see how much content you covered in just an hour. I know like this to study by yourself takes a lot of time, so I believe the audience has a lot homework to do. Like you have to go off and study this in
Yeah.
your free time. This was quite dense material.
Yeah. Like even going through Blurr and stuff, it's hard to kind of, I mean, it's been weeks and weeks of, development just for those things that we just looked at, real quickly. So, yeah, look at the source code. And I know something like that's always something that Jeremy's, encouraged with Fast AI. And, the more you look at the source code, then the less foreign it looks. And then the ideas just become, more clear. And so go through that difficult task sometimes. And hopefully what I put up there isn't that difficult.
Definitely. There's one critical comment. I believe they're trying to understand why are we using Blur and not pure Fastai. My understanding is there's a few things that you can't do in Fastai, which is why you need Hugging Face, and then Blur is this nice bridge between both of the worlds. And there are some opinions from Wade also that make their way into there. Like you were looking at the different classes that Wade was walking us through. There was hinting that's we don't see, I think, that in the Hugging Face source code. It might have changed since the last time I saw it, but the question is, why are we using Blur, or what advantage is there for using Blur?
Yeah, so if you want to just use Fast AI, a lot of the stuff that you'll see in Blur are things that you're going to have to code yourself. And some of the reasons why Fast AI out of the box just can't be used with Hugging Face is because of how tokenization is done. So in Fast AI, you have like ULM fit, which is a traditional, kind of language model, and it's an entirely different architecture than the transformers. And then the way that the transformers, the models actually, the inputs are different than what you see in Fast AI. So in Fast AI, it's very position based, and you pass in tensors, whereas with transformers, you pass in dictionaries with the different things, so like the input IDs, the attention mask, and so forth. And then also when you use a Hugging Face transformer model, the outputs are different than you would in Fast AI. And so like they actually have like a model outputs object. And so for token classification, there's actually a start logits and end logits that you can look at. Whereas with Fast AI, you're typically getting things just very positional. So you're just getting a value, but you don't know what it relates to. And also, some of the other work is just in terms of encoding and decoding different types of text. So like if you look at Blur, you'll see that a lot of work's gone on the show batch. Like how do you show predictions? How do you show batches or show results? And it varies per task. So sequence classification looks different than token classification, than question answering. And so those are some of the things that if you wanted to have those abilities, you'd have to code them yourself. So there's nothing, if you look at the Blur code, it's really, I'm using these Fast AI concepts, callbacks all over the place, and transforms.
Yeah.
But if you didn't want to use Blur, you would have to essentially create these same entities.
You would have to write Blur again by yourself.
Yeah, you just write another version of Blur, with call it something different, Fast Blur or whatever. I don't know. But yeah, so those are some of the main reasons why kind of Blur has to sit in there, at least with version 2 of Fast AI.
That makes sense. I hope that answered the question for, I think it's an anonymous user because they're using a pseudonym. Awesome.
Yeah. No problem. If people have other questions, yeah, like I said, you got my Twitter handle over there. Send me a DM or shoot me an email. If you go to omeow.com, you can find all my other contact information.
Amazing. Thanks again for your time, Wade. I believe we're still meeting next week, but the week after we'll be taking a break since Wade will be on vacation.
I think we're doing
Uh,
2 weeks. It's
so,
the 13th that we'll be taking a break. So
so
next week,
we're still meeting next week, I think.
next week we're gonna finish up token classification and get into training and inference, and then the following week question answering.
Amazing. So we're still meeting next week, and then we'll have a 2 week break. I'll request Wade to have enough homework to keep us busy then.
Oh
But
yeah, no problem. You got it.
thanks again for your time, Wade, and I look forward to learning from you again next week.
All right, good being here. Thanks again, Sanjay.
Thanks for joining, everyone. We'll see you next week.